Hey everyone, welcome to more calculus, and today we're going to be looking more at the fundamental theorem of calculus. Of course, we're taking it from the approach of a constructive side. In other words, we're kind of learning how to do this or what it all means. So keep that in mind if you're watching this from somewhere else. We are in the process of trying to figure this out. So let's head on over to our screen here. We've got Triceratops, genus Triceratops. Is a large quadrupedal, plant-eating ceratopsian dinosaur that had a frill of bone on the back of its skull. Most of you probably know a Triceratops by now, of course. Fossils of the three-horned face, as its Latin name is usually translated, date back to the final 3 million years of the Cretaceous period, 145 to 65 million years ago. So, we're talking about 62 million years ago to 65 million years ago for the Triceratops, making this one of the last non-avian dinosaurs to have evolved. Paleontologists estimate that the body length of the Triceratops approached 9 meters, about 30 feet, and the largest adults are thought to have weighed 5,000 to 7,000 kilograms, or 12,000 to 16,000 pounds. That's a heavy, big animal. So our exploration, we're going to start with this concept of the accumulator function f of x as defined by capital F of x. Now I know it's kind of confusing to have f of x and f of x, so I'll say big F and little f. Hopefully you'll figure out which I'm talking about with that. So we got big F is the integral from a to x of little f. A is a constant, and what we're going to do is take the derivative of both sides with respect to x. Here on the left side, the derivative of big F is just f prime, big F prime. And then here on the left side, we're going to take the derivative, but we're not really going to take the derivative. We're going to say we're going to take the derivative. And then now that we have that set up, on the right side here, we're going to use the limit definition of the derivative. So what does it mean when we take the derivative? It means that we're going to take a limit as some quantity known as h goes to 0, and then we're going to evaluate our function with f of x plus h minus f of x. But of course, we don't have f of x, we have an integral. So maybe using the word f is probably confusing here. So we're going to substitute x plus h for our upper limit, and then we're going to subtract it for substituting x for the, well, actually not doing any substituting at all. So what does that look like? So here's what we mean. We take the same integral that we have here, and we're substituting x plus h for x in the integral. So that in the function, really. So this is the limit definition of the derivative. It just looks kind of wonky because you're trying to use the limit definition of the derivative on an integral, which leads to some very unwieldy looking notation. Okay, so the next piece here is I want you to look specifically right over here, this part right here. Okay. If we were going to look on a number line, you would see a over here, and then you would see x here, then at the very end you'd have x plus h. This is kind of assuming everything is positive, but it doesn't really need to even be that way. If we have a, x is someplace to the right of a. If I add h more, then I get an x plus h. So what we're doing is we're going to break apart this integral using rules, additivity of integrals. So remember, the integral from a to b plus the integral from b to c is just the integral from a to c. Well, in our case over here, we're saying a is, well, of course, a, and this is b, and then this is c. So the integral from a to x plus the integral from x to x plus h is the integral from a to x plus h. And when we put that into our integral, it kind of looks like this. The integral from a to x plus the integral from x to x plus h equals the integral from a to x plus h. So you can imagine we're going to take this piece right here and we're going to we're going to take this piece right here in red and we're going to substitute this over here. Just like that. So our f prime of x, the equation that we have over here, that's going to get transformed into this beastly looking equation over here. Let's take a look at what I'm sorry, I forgot that there is a limit here as h approaches 0. But let's see what happens here. We got a to x of f of t. We've got x to x plus h of f of t, and then we have minus a to x of f of t. So this and this right here, those two, they cancel out. So when you cancel them out, f prime of x is going to look like this, where we have the lower limit is x and the upper limit is x plus h. So let's carry you through that one more time. We've got if f of x equals this accumulator function, f prime x equals the derivative of the accumulator function. And if I take the derivative of the accumulator function, I can then again also turn the accumulator function into the limit derivative, the limit definition of the derivative. So f prime is equal to the limit definition of the derivative. And then if I break up this integral over here from a to x plus h, I can cancel out and get to this equation over here. So that was a lot of stuff there, really. Okay, so the derivative of f prime is just 1 over h multiplied by the integral from x to x plus h of f of t. And that's supposed to remind you of the mean value theorem, where if you take the derivative, or if you have a function somewhere between where you have f of a is less than f of c is less than f of b, well, that's not the part that's supposed to remind you. The integral is supposed to remind you. We have an integral of 1 over b minus a, integral from a to b. So from what I'm seeing, we're saying a, this a right here, that's going to be equal to x, or b is going to be equal to x plus h up over here. So when we substitute into our mean value theorem, we're going to get 1 over b, which was x plus h, minus a, which was x, multiplied by the integral from x to x plus h of, well, our integrand was f of t dt. When you do that, that's just equal to 1 over h integral of f of t dt. Integral runs from x to x plus h. So you see why we say that looks a lot like the mean value theorem. Okay, and of course a is x, so a is x. Let's highlight that. A is x, and b is x plus h. And the upper and lower limit here, well, that should just be x to x plus h. After that, we're going to apply a limit over here. So the limit of f of c equals the limit of 1 over h integral from x to x plus 1. And if all of these things are equal to each other, then that means that f prime of x equals this limit as h approaches to 0 of f of c. Wow, I mean, that's some pretty heavy stuff here. We're going to keep going here, and let's remember that f of c had to be between f of x and f of x plus h. That's right over here. Okay. Those two statements are the same thing, and this was our condition for the mean value theorem. If you were going to apply a limit to all three of them, so you can get that limit as h approaches 0 of f of c, look what happens here. You've got the limit as h approaches 0 of f of x on the left side. On the right side, you've got the limit as h approaches 0. And if h approaches 0 on the right side, this becomes the limit as h approaches 0 of f of x. Well, really, f of x plus 0. So you got the left side here is f of x. The right side is f of x. So the middle, by squeeze theorem, that's got to be f of x also. And so when you put that all together, that means that capital F prime of x is equal to little f of x. Which I admit doesn't sound very overwhelming until you take a look at where we started. Okay. We started with f is equal to this accumulator function, the integral from a to x of little f. And if we took the derivative of both sides, f prime of x, okay, and we took the derivative of the accumulator function, well, look at that. The derivative of big F is equal to the integrand. Okay, so what this says is the derivative of a integral is the integrand. Of course, that's not the only story here. Something else had to happen in order for that to be true. And in order for that to be true, your upper limit here needed to be a variable. It needed to be the same variable that you're differentiating for. So under those circumstances, if you have a variable in the upper limit and you're taking the derivative with respect to that same variable, then the derivative of the integral is the integrand. So we're going to take a look at a couple of those problems. Let's take a look at letter A. It's done for you. Okay. So if f of t equals cosine t, a is equal to negative pi and b is equal to x, negative pi and x are up here. So f prime of x is just equal to the integrand cosine x. Okay, so let's do the same thing with letter B. Letter B, we're taking the f prime of x. Okay, it does say find f prime of x. That's equal to the derivative with respect to x of the integral from 2 to x of 1 over 2 plus e to the t dt. Notice what happened. The variable of differentiation is equal to the upper limit of the integral. It is the same thing. It's literally x. So when that happens, all you need to do is substitute that upper limit into the integrand, and you're done. See, it's really an easy problem if you look at it through the correct lens. Look at letter C. We have f of x equals the integral from x to 5 of 2t sine t dt. Okay, so what's the problem here? Well, when I take the derivative d dx of the integral from x to 5, well, there's problems now because you will notice that the variable for differentiation, now it appears as the lower limit. So, what do I do? Well, what you need to do is use some of the properties of integration. something you can do to get x into the upper limit. And the way to do that is just to reverse the limits at the cost of the negative sign. So now we're going to integrate from 5 to x with this negative sign in front. Okay, so we've reversed the limits, and now we notice that x, the variable of differentiation, is the upper limit. So we are free just to substitute. So it's equal to negative 2x sine x. And we're done. Okay. There's really no problem in these problems for the most part. Okay, we'll definitely see more of this later, but now let's see what happens if we attempt to use the chain rule here. So when I look at this, like I looked at the previous one, I see the variable of differentiation is x, and the upper limit is x squared. Well, it's not a simple variable. Not a simple variable. Okay, so what we're going to do is we're going to make a substitution. We're going to say u is x squared. So instead of an x squared, we change that to a u. All right. Well, what's the cost of doing that? Well, if I'm still going to take the derivative with respect to x, I'm going to have to take a derivative with respect to u and then multiply by the derivative of u with respect to x. That is the chain rule. Down over here, we have the integral, the derivative with respect to x of the integral from 1 to u of cosine t. That's the derivative with respect to u from 1 to u of cosine t dt multiplied by du dx. If I color code this carefully, you can see that this first derivative with respect to u is the derivative of the integral, and the second derivative, du dx, that's the blue integral. So all of those pieces are the same thing. Now, let's see. Derivative of, what is the d du, the derivative with respect to u, of cosine t? Well, this time, the lower limit and the upper limit do match. So all I need to do is substitute u into the integrand. And then I have to multiply by du dx. Well, what is du dx? Well, if u was equal to x squared, then du dx is just 2x, which is what you have down over here. Finally, you're going to substitute u for x squared over here, and there you have it. Cosine of x squared multiplied by 2x. Let's try that for these. Okay? For part A, if I take the derivative with respect to x from 2 to x cubed of et dt, first of all, let's see, do the limits match? And I got an x squared and an x cubed. No, they do not match. So I'm going to do a substitution. I'm going to say u equals x cubed. And now my derivative looks like this. The derivative with respect to x of the integral from 2 to u et dt. Okay, well, that's getting closer. I'm going to use a chain rule now. So in order to do this derivative, I'm going to take the derivative with respect to u from 2 to u of et dt. And then I'm going to multiply by du dx. Checking again, the upper limit matches with the variable of differentiation. So this is just equal to e to the u. And then du dx is, well, the derivative here is 3x squared. So when I make my final substitution, u is the same thing as x cubed. I get 3x squared multiplied by e to the x cubed power. There we go. Not that bad. I don't think it's that bad. Definitely a little more into it than the previous ones we did. Now f is not going to fool me again. Notice that the derivative is in the lower limit. So I'm going to try to speed things up here, and I'm going to say u is equal to sine x. Of course, that means du dx. That's going to be equal to cosine x. And so f prime of x is going to be equal to d du. I'm going to switch the variables at, I'm going to switch the limits at the expense of a negative sign. So now 0 is in the lower limit, u is in the upper limit of natural log t dt multiplied by du dx. Okay, so that was a whole lot of things I did there. Maybe I should have gone slower, but yeah, let's do it anyways. Okay, what else can we do here? Oh yes, this, since u matches with u, we get the negative of natural log of u multiplied by du dx, which was cosine x. And finally, this is the natural log of sine x multiplied by cosine x. Okay. B is a difficult problem. That would be rated, I see it year in, year out in the AP exam. A problem like this would be rated as very difficult because there's this chain rule to deal with, and then there's also a variable switch that, or not a variable switch, but a limit switch that needs to happen. So if B is difficult, that must make C super difficult. And the trick for C is you're going to look at g of x as the sum of two integrals. We're going to say from x to a of sine t dt plus the integral from a to x squared of sine t dt. So I'm going to try and do this as quickly as I can. So the first step, of course, is to think of this as that variables, the switch of the upper and lower limit, sine t dt plus the integral from a to x squared of sine t dt. And when you know what you're doing, this becomes super fast. Look, upper limit is x, so I don't need to do anything special. I don't need to do anything special. I really should say g prime here. G prime of x. That's x, nothing special. So this is negative sine of x. And I take a look at the second one, and I've got x squared. That is a little bit special. So I'm going to substitute that x squared, and I'm going to multiply by the derivative of x squared. So when you throw that together, g prime of x is equal to 2x sine of x squared minus sine of x. So that would probably be rated as extremely difficult. Moving on, we've got the fundamental theorem of calculus over here. Basically, you're just substituting the derivative of the integral is the integrand, but pay attention to the limits. Know your limits. Okay, and by know your limits, of course, I mean pay attention to the upper and lower limit of the integral, because that's going to dictate what you do. Let's check our understanding. The length of a triceratops brow horn is approximately given by this function L of x in feet, where x is the number of years since birth. So x is the age of the Triceratops, and L is the length of the Triceratops brow horn. We're going to use the fundamental theorem of calculus to find the rate at which the Triceratops brow horn is growing when the animal is 2 years old, the rate. So if the length is given by L, we're going to be looking for L prime of 2. Okay, so we are doing well, what variable do we need to do, d dt or d dx? And based on the fact that we're looking at with the animal being 2 years old, x is equal to 2. So we're going to take the derivative with respect to x. So L prime 2 is going to be the derivative with respect to x of the integral, which is 0 to x 0.068 10 minus t dt, and we're going to evaluate that when x equals 2. So always take the derivative first and then find the integral. Or, sorry, derivative first and then substitute. Never in the opposite order. Always substitute after you take the derivative. So I'm looking at the derivative now, and I see that my variable of differentiation is exactly the same as the upper limit, which is what I want. So I can just substitute that upper limit in. 0.068 10 minus x. Evaluate that when x is equal to 2. And we get that L prime of 2 is equal to 0.068 multiplied by 8. And I don't know what that is. I'll ask Siri. Sorry, I don't have a Siri. I have an Alexa. Alexa, what is 0.068 times 8?
0.068 times 8 is 0.544.
There we go, 0.544, and we're doing feet over here per year. Feet per year. So every year, or when that Triceratops is 2 years old, its brow horn is increasing by half a foot every year, 6 inches roughly. Okay, so that was our 6.4, our investigation into the fundamental theorem of calculus. Hopefully this clears up some misconceptions about taking the derivative of an integral, and if you're doing this in the future, sometime near the AP test, I hope this is very helpful to you. So, signing off for now. I'll see you later. Have a good rest of your day.